Hello everyone. Sometime back, I showed you a hand crank power generator that uses a DC motor with a belt pulley driving system. Today, I'm going to show you another hand crank power generator that uses a stepper motor. The biggest advantage of using a stepper motor is that you do not need any belt pulley driving system or gear mechanism to increase the speed of the shaft. The shaft can be directly driven. Here I can show you how simply one can make such a hand crank power generator. So all you need is a bipolar stepper motor, a flanged coupler, and the aluminum plate, and a long screw, and a hollow aluminum pipe for easy cranking. So that is why you can build your own, and it is cheaper and simpler. And at the output, this should go through some process to better use of that generator's voltage. And additional advantage of using a stepper motor is that you are getting AC instead of DC. So you can use easily voltage doubler if you need higher voltage, or your stepper motor is not generating much. You can easily use a voltage doubler to for some other applications. So I'm going to explain how to choose a suitable stepper motor for the purpose of hand crank generator. The biggest advantage of using a bipolar stepper motor instead of a DC motor is that the stepper motor shaft can be directly driven with a hand cranking mechanism to get 5 to 15 volt. There is no need for a belt pulley or speed enhancement gear. There are various sizes and types of stepper motors. I will consider only bipolar stepper motors of sizes NEMA 23 and NEMA 24. The shaft diameters are usually 8 mm and 14 mm respectively. Inside the motor, there are two coils. One is called phase A, another phase B. A permanent magnet rotates inside the stator. In usual motor applications, variable currents are applied to these coils, which creates variable magnetic field, which in turn forces the magnet to rotate. Reversely, if we rotate the magnet rotor, a variable magnetic field is created, which induces voltages on these coils. The generated voltages are AC and they have phase differences of 90 degrees. We can connect a hand crank with the motor shaft. Driving directly, we can generate 5 to 15 volt easily. This is sufficient to charge the mobile devices, laptops, 12 volt lithium ion battery pack, and even an auto battery. The usual hand cranking speed is 75 to 200 rpm. We can say 150 rpm to be the moderate speed. Some people can even reach higher than 250 rpm. Higher the rotational speed, higher the output voltage, and also higher the output frequency. From the manufacturer's data, we can find our suitable motor. Usually these are the data you will find: phase current, steps per revolution, resistance per phase, inductance per phase, and holding torque. So for initial selection, we need two data: the holding torque and the phase current. Holding torque is expressed by a number in Newton meter and the phase current IP by ampere. There is another important term called torque constant, Ke, which comes with any stepper motor and Ke can be expressed by this equation. If we know holding torque and phase current, we can easily find out the torque constant. And the angular rotational speed, usually expressed with the term called omega, radian per second, and omega can be expressed by 2 multiplied by pi multiplied by rpm divided by 60. So if we know rpm, we know omega. So if we plot rotational speed versus output voltage, and if we know the torque constant, and we know that the approximate hand crank speed is 150 to 200 rpm, we can easily find out what's the voltage, output voltage we can get. I am going to analyze manufacturer's data for several motors and try to show the suitability for this application. I am considering 3 motors from Oriental Motor and 2 from Amazon. I am going to divide holding torque by phase current for each motor. As you can see, these motors, for these motors, the calculated numbers are 1.7, 1.02, 0.6, and from Amazon 0.93 and 1.3. So for the rotational speed of 150 rpm, on the x-axis I am taking a holding torque by phase current, and on the y-axis output voltage. You can see for this motor, Oriental Motor, holding torque by phase current is 1.7. We can get the output voltage 17 volt. For the other motor 102, that is close to 12 volt, and the lowest is with this motor 0.6, and we can get little over 6 volt. As the output voltage from the bipolar stepper motor is AC, we have to rectify it, and furthermore the cranking is not uniform all the time. The output voltage varies with the cranking speed. If we want to make sure the output should never exceed 5 volt or 12 volt or whatever we want, we need a voltage regulator as well, along with the rectification and filter. Due to the rotation of the magnet rotor, voltages are induced on both the phases. 2 Schottky diodes can be used to rectify and then combine the resulting DC voltages like this. An additional filter capacitor will make the DC smoother. As I mentioned that I am going to use these 2 different motors as generator. One has a higher holding torque by phase current ratio, and the other one is less. With a moderate rotational speed of 150 rpm, we can see that we can easily generate more than 12 volt with the first one, which is suitable for the most of the DC applications. The other can generate approximately 6 volt, which is only suitable for USB type charging. For the first motor, we can use the type of rectification as mentioned in the earlier slide. For the second motor, this one, we can use a voltage doubler at the output to utilize the output for DC more than 12 volt applications. Let us see how doubling of voltage occurs for one phase. Peak AC 8 volt is generated. The positive half cycle should pass through the top diode and charge the capacitor C1 as shown. The negative half cycle will go through the second diode and will charge the capacitor C2. At the output, we get the sum of the voltages C1 and C2, If the AC peak voltage is 8 volt, there is a little drop across the diodes and the output voltage will be around 15.2 volt. In practice, two such doublers will be used for two phases. The outputs are combined and further filtered by another capacitor. As I mentioned, that the generated output should go through a voltage regulator. We can use either a linear regulator or a switching regulator. Linear regulator is simple but less power efficient than the switching regulator. Here I am showing a schematic of a linear regulator that you can use at the generator output. By adjusting the resistor R2, you can adjust the required output voltage. As the regulator chip LD1085 operates in the linear mode, if you draw more than 200 or milliampere or so, you need a heatsink as well. The generator output can also go through a switching regulator that is shown here. This type of regulator I previously used in another of my project, hand crank DC generator project. Changing just one resistor, we can change the output voltage 5 volt or 12 volt. Now I am coming to the mechanical construction. Besides the motor, I need some hand cranking mechanism for direct drive. I bought two flanged coupler like this from Amazon, one with diameter 14 millimeters and another one 8 millimeters. The values I choose considering the shaft diameter of the two widely popular stepper motors. One is NEMA 34 and another NEMA 23. NEMA 23 motors are usually cheaper to buy. I used aluminum plate of 5 millimeter thickness and 20 centimeter long for the cranking. 3 additional holes are made on the aluminum plate to place the largest screw for the handle. I can switch the screw in different holes to find a suitable position for cranking. We need several M5 screws to attach the flanged coupler on the aluminum plate. A 5 inches long and 1/4 inch diameter screw is used as part of the handle. On this screw, part of the hollow aluminum pipe is inserted for easy cranking. The bolted flanged coupler and the aluminum pipe is shown. The whole cranking system is shown in this photo. Motor shaft should be attached with this flanged coupler. As I mentioned before, I am going to test cranking with two different stepper motors. One is the big one, another is small, NEMA 23 and NEMA 34. First I'll try with the bigger motor, then I'll replace the flanged coupler and use the smaller motor. I am cranking the motor and the generated AC output waveform is shown in the oscilloscope screen. 3 different waveforms are shown for 3 different cranking speed. At low speed, 75 RPM, the peak output voltage is 10 volt and the frequency is 62 Hz. At 150 RPM, the peak voltage is 20 volt and the frequency becomes 125 Hz. At 207 RPM, peak voltage reaches 27 volt and the frequency is 172 Hz. I connected a 12 volt lamp with one phase and started cranking to see how the lamp glows. I also connected a regulator at the output to charge a cell phone. I replaced the flanged coupler and started to use the smaller NEMA 23 motor. As the output voltage is lower with this motor compared to the big motor, at the same cranking speed, I used a voltage doublers, as you can see on this small circuit board. Output voltage is measured with a load connected. The doubled output is connected to a regulator, and then that is being used to charge a 12-volt lithium-ion battery pack. Bipolar motors have two coils, and each coil has some resistance. Furthermore, as the magnet rotor rotates, voltage is generated in the coils. The frequency of the generated AC voltage will also increase with the increasing speed. So if we want to know the output voltage and load current relationship, we have to consider the impedance of the coil. With load current, voltage drops due to this impedance. For this smaller motor, if we use voltage doubler, we are getting twice the output voltage. However, with increasing load current, the voltage drops faster. This is because the generated power becomes the same. We are getting double voltage at the expense of current. I'm going to show two of the motors which are suitable for this project and available in Amazon. This one has a sufficient torque and phase current, and you can also see the data sheet. You can see 3 ampere phase current and the torque is 2.8 Newton meter, so quite good for our purpose of hand crank power generator. And another motor that is this is also good, a little more expensive, but it has a higher phase current and the torque as well, and some of the data is also written on the back side of the motor. I'm going to use two motors for this project, one big and another small. This small flange coupler can be replaced and the small motor can be connected easily. And now I am testing the big motor with the crank, and a oscilloscope signal is, you can see it is changing as the motor is speeded up. Higher the voltage and higher the frequency, and as the speed goes down, frequency and voltage both goes down. Now both the outputs, phase A and phase B, are connected with a diode, with two diodes, and you can see the waveform is a little different now. Now I connected a 12-volt lamp, and you can see it is glowing. Now the output is connected to the to a regulator, and output goes to the cell phone, and you can see the 5.4 volt fixed is being established at the output. Now a 12-volt battery pack is connected at the output of the regulator, and you can see it is charging, and the output voltage you can see on the meter. Now the big motor is changed and the smaller motor is in place, and you can see a voltage doubler is at the output, and that output goes to the load lamp. Lamp is glowing, and you can see the voltage of the motor. now the output of this doubler is connected to the battery pack. You can see the battery pack is charging.